So let's continue with the pricing example and discuss, how does one actually price this type of option, this type of contract in a financial market. So, option at strike K, you have a maturity T, and you if you buy this, you get paid by the amount at which the price of the underlying stock exceeds the strike K. And so we're faced a decision to buy this option at some price C0. The C usually it's convention for what's called a call option. This is in fact it's called the European call option, and there are many different types of options, including American, Asian options, various exotic options that are very difficult to price. This is the simplest kind of example that you see out there. And so what happens if we compute our expected payoff? Well, this is how we would do it. It would be very similar to the way we carried out the calculations for the mean and variance. And if we were faced with the decision to buy this contract at a price C0, we would ask, well, is our payoff more than its price? Because if it's more than its price, it's sensible to then buy the option. And if not, then not. And if you're conversely, if you're the seller, if you're the seller of this option, then this is kind of how much you're on the hook for at the end. This is how much you actually pay at the end. And so you sell the option and you make the price. This is your profit at time 0. And at a time t later, this is how much you stand to lose. And so you also compute the expected payoff, but now you want it to be less than the price, because you'll sell the option, you'll make this amount, and you in expectation want to be paying less than that. And so finally, kind of from these two arguments, the fair price for the option, what doesn't, the price that doesn't favor neither the buyer nor the seller, is just this expectation. And so this is how options are priced by similar arguments, and this extends to many other financial instruments. And you can kind of go to various exchanges where they sell options. The CBOE is one, Chicago, I guess, Board of Options Exchange, and you can see kind of various prices at different strikes, and depending on what model you have, you'll be able to kind of see whether the prices are something that's kind of favorable with respect to your decision whether to buy that contract. And so now I guess we could do is sort of suppose that we bought the option, we paid at time 0 some price, and now we're sitting there just kind of it's just kind of waiting until we make the big bucks. And so I guess the calculation that I want to introduce now is this one. So why would we be interested in that conditional expectation? So you're sitting there and time is passing. You had time 0 here, and you're observing the price up to time t. And so what this VT is defining is in fact the value of this contract given some extra information that you've just had. You've purchased the option, and now you can kind of tell how is its value changing. And if that value is dropping, you could come in and try to mitigate or offset your risk somehow. So in finance, this is called hedging your risk, and you can learn all about this if you take a math finance course or anything in risk management. But here our goal is going to be to just motivate the fact that this is an important calculation, which obviously it seems to be. It also seems very difficult because we're conditioning on essentially infinitely many random variables, and so it seems a bit of a non-starter. But I'm going to try to convince you that if we have the Markov property, then the calculation becomes much more manageable. So just very quickly, if once you have this price here, it's a function of the Brownian motion W, which has volatility sigma, and here I'm just doing nothing else but computing its expectation, expectation of a function of G of the Brownian motion at time t, and G can be anything here, and in particular you can write it to match the what we're taking, that random variable inside of this conditional expectation here. And if this statement is true, meaning that if we can actually replace this conditioning by only conditioning on the very last observation of the Brownian motion, then we're in much better shape. In particular, here, if this is the statement of what it means for the Brownian motion to have the Markov property, and this probability on the right is basically the transition probability of that process. It starts off at some time s, and we're looking at the probability that it enters some set a. This is a subset of the real numbers at time t, and so that sounds exactly like a transition probability, similar to transition probabilities for Markov chains. So if the Markov property holds, then we have we could try to compute these conditional probabilities, or we could try to package them as transitional probabilities, and then we could actually compute this expectation by writing an integral in this form. That's exactly what this conditional expectation is really representing here, with the only exception that this x here would be representing the place where I've started. So this would be sort of a transition probability from x to y. I'm integrating over all possible places where, in this case, wt could be. The value of that I'm trying to find the expectation of is g of that y, integrating over all y, and starting at ws, which is what I've called my x here. So you kind of can see a very with the Markov property and with these transition probabilities that we're going to talk about, you get access to these kind of calculations, and in particular you can try to find out the value of your option at any time before maturity. So little t there is smaller than t, and then you can sort of make some decisions to potentially offset some of the risk that you're facing. So maybe before I dive into the Markov property and convince you that it holds, we've sort of sketched that out very briefly at the end of the very last lecture. Before that, let me maybe talk about what this transition probability is. So if we get an expression for these transition probabilities, then we know how to compute these conditional expectations, and certainly more complicated ones like that over there. And so what I've written here on the bottom is I've picked up from this side of things. So I've picked up from this probability and taken the event that I'm looking for, Brownian motion in some set A, and I've written it in this form. And here you can see that ws cancels. I've basically added and subtracted the Brownian motion at time s, which is a common trick, and w0 is just it's 0, so it doesn't change anything at all. The reason for doing this is because we know the Brownian motion increments are independent, and so that's a sum of two independent things. And I'm also conditioning on ws, but that's equal to ws minus w0, which is another increment. And here I'm just, because I'm conditioning on it, I can kind of claim to know what the value is, or I can just say suppose we're given that it's equal to x, what is this probability then? And to compute that, we kind of go through the usual steps. We look at those two things that we're adding. The first one is an increment from t to s. That's normally distributed with mean 0 and variance sigma squared t minus s, or h, what I've labeled here as h. That is the distribution of that increment on the left there. And the second increment, we know that's just x. So that's taking our mean 0 normal distribution and shifting its mean over to x. And so the distribution of this entire random variable, given that I know that the second part is equal to x, is just normal with mean x and variance sigma squared h. And that's exactly what this density represents. And I'm integrating over the set A, because that's what that's the probability that I'm actually computing. This is what would now be called my transition probability. This is the transition probability for the Brownian motion, transitioning from state x to state y. Both are real numbers, and I have h units of time to do so, and this density takes this form. So now, what we need is, if we want to compute a conditional expectation like this, or the one up there, we would follow this, exact strategy. So, this integral may not have, may be difficult to evaluate explicitly or analytically, but, certainly, on a computer, you can kind of use numerical integration to then, you know exactly all of these terms. Presumably the g function that you're trying to integrate over, and we now just discussed how to get our transition probabilities p x y's, and so then this is where you start, and you kind of can evaluate what the integral is. So as the last kind of piece, let's discuss why the Markov property of the Brownian motion holds. And we've seen that this process w delta t, this was kind of an approximate Brownian motion where it would move in these small displacements delta x. It would move up or down. It would do so in little time intervals delta t, and we took both of those to 0 in a special way. We took wx and wt down to 0 and argued that the limit, this kind of the idealized limit, the idealized process, is in fact the Brownian motion, and all of the properties that this had carried over to the Brownian motion, to the limit. And so, for example, the path of this is continuous, and therefore the Brownian motion, the limit of w delta, is continuous. We also saw that the increments of w delta were independent, and therefore the increments of the Brownian motion were independent. There's a little bit of a caveat there, but I'll skip it. But so we argued for this at the end of the last lecture. And I think the last thing we mentioned there was that the increments were also stationary for w delta, and therefore the increments of the Brownian motion were also stationary. And so the same exact kind of steps would lead us to conclude the Markov property for w from starting from w delta. And here's how this would work. So I would basically try to write out what this probability is and what this probability is, and show how to compute it. And if those two calculations lead to the same value, I conclude that these two sides are indeed equal. So if I start out with this left-hand side, I can write w delta t like this. So remember that w delta t is a sum of independently distributed, independent and identically distributed increments xj. These were random variables that took values plus or minus 1 that determined where our random walk was moving. And starting from ws, this is how I'm decomposing the path of w delta. I've essentially said let w delta t be decomposed into w delta s plus the remaining trip. So if you want to look at it on a diagram, I'm looking for w delta t, which I guess is here at this time. I'm looking for it to be in a set A, and what I'm saying is that w delta t, which is this value, is nothing other than taking w delta s, which is the sum of all the increments up, all the increments xj from 0 to time s, and add on to that all of the increments in this time. So the xj's lying between s and t are summed up in this sum here, and those are the ones that compose this part of the path. And so what does this conditional probability really look like? Well, it looks like we definitely need the value w s. We knew that was going to happen. We're going to have to rely on, from all of the random variables in here, we're going to have to rely on this one, w delta time s. But the rest of the path, everything that's in the sum, everything in here, is completely independent of everything that happened before, from time 0 to s. And so, the only thing we take, the only thing we gain from all of this conditioning is, w delta s. And this establishes how the calculation would run starting from this side, and you can do the same thing starting from that side and claim that the two are indeed equal. And then w delta has the Markov property, and then with a few more technical details, we would take w delta and delta t and delta x down to 0, and we would establish this relation, which is the Markov property that led to our transition probability. So hopefully you kind of see sort of all of the all these ingredients kind of coming together. Just sort of the brief summary in terms of what to take away. The Brownian motion has the Markov property, which is this statement right here. It allows you to compute conditional probabilities as such, where the complicated conditioning, where we observe perhaps some price or something related to the price over continuous time, can be removed and replaced only by the most recent observation. And this conditional probability can further be evaluated against this transition probability kernel, and that transition probability is given by a normal density. So now computing these things is not a big deal, or at least writing a clean sort of way, a clean path to computing them numerically. And then the same thing would hold for applications such as the options contract that we've been discussing.